Welcome back, everybody. We are sitting in our next session, which is going to be all about going over the exercise set that you've been sort of noodling on for the last 40 some minutes or so. Hopefully, you've been able to take a little break as well, stretch, walk around a little bit, do all those sort of fun things to keep the blood flowing. But also be able to dive into some of these examples and exercises to see if what we've been talking about has been sticking. So I think we should probably just dive uh, into these questions. Again, sort of the range of what is mentioned in these questions is sort of encompasses the entire first day. There are things about from earlier sessions of videos, from the intermediate modeling video, from Asan's talk on optimization versus heuristics, and all the way through the notebooks and everything. I've tried to hit on everything here a little bit at least. So yeah, let's look at question one. Some of these multiple choice questions. Question one is regarding some of the earlier stuff that we talked about. All projects that can utilize mathematical optimization identify this well in advance. So everyone has a crystal ball and knows when mathematical optimization is going to be there and when to use it. That is clearly false. Um, as we mentioned at the beginning of the intermediate modeling video, we mentioned that sometimes you have to go hunting for optimization problems, sort of listening to what people are saying, listening to the problem that they're describing, and seeing if it checks enough of the boxes of what mathematical optimization does for it to be a good fit for a problem. And we also talked about ways that people sort of don't necessarily grasp on optimization sort of right away, and they may need a little bit of push in the right direction. So yeah, it's definitely could be an issue for some projects, and it's a good thing to be able to understand, again, what those key components are of optimization. So then when you see them, even if they're not sort of clearly sort of just presented to you on a silver platter, then you're able to understand what they are and have a successful project. So question two, give myself a little bit more room here. There we go. Question two, the core value of machine learning lies in the blank used to fit models. In mathematical optimization, the blank carries most of the value. And the correct answer to this is B, data and algorithms. The data is essentially the lifeblood of machine learning, and it was popular to say, a few years ago that data is the new oil, and make sort of claims like that. So essentially, yeah, everyone was focusing on the data in machine learning, and rightfully so. That is the driving force. The algorithms and the processes to fit the models are not really that super complicated. However, in mathematical optimization, the opposite is true. The algorithms, the special sauce, the secrets in the library, are that's the important part. That's the difficult thing to do, is to actually solve these problems. It's easier to formulate a mixed integer program than it is to solve it. And that's why solvers like Gurobi are very much needed, is because we have the algorithms, have the processes, have things figured out enough, at least, to be able to efficiently solve a lot of these large problems. So on to question three. Heuristics often have a way to know how far a current solution may be from the optimal solution. So this is definitely false. Again, heuristics do not really have any way of understanding what an optimal decision is. There's no qualifications for it. There's no criteria. It's just, hey, this is pretty good. So if a heuristic can't even describe what an optimal solution may look like, there's no way it can describe how far a current solution may be from that. And again, as we mentioned in a couple of sessions and several times in Opti101, the fact that mathematical optimization, when it pops out a solution, guarantees a feasible solution, so something that's actually doable given your constraints, and something that is globally optimal, is a very important and very sort of unique thing that you can get in problems that assist with decision making. Let's see. So, on to question 4. While it is good to note the size of a mathematical optimization problem in terms of the number of variables and constraints, it is far from reliable. It is far from a reliable way to measure how long it will take to solve, and that is true. While there do exist problems that have hundreds of thousands or millions of decision variables and hundreds of thousands and millions of constraints that may be difficult to solve. There are still you can find you can find other examples where you have hundreds of thousands of millions of variables, hundreds of thousands of millions of constraints that are problems that are easy to solve. So it really isn't a great indicator for the difficulty of a problem that is to solve. There are other things that are more important, sort of like the structure of the problem and the way that it's formulated. There are things that can happen within that really make problems difficult to solve. And a go-to example for this is the traveling salesman's problem, which isn't a relatively it's not a relatively large problem when you have a decent number, even if you have a decent number of cities. And if you're not familiar with the traveling salesman problem, it's you have a set of cities and you want to travel to each one once. What's the sequence that minimizes the total distance? That's not really, again, it's not a super complicated problem, and the size of the problem is not astronomical compared to other problems, but it is one of the hardest ones to solve, and there still isn't really there are some specialized algorithms that do a good job at solving this problem, but again, it's still not something that is super easy. So long and short of that is don't pay attention necessarily to only the size of a problem in terms of variables and constraints. There are other things at play. So now let's move on to the free response section. And I do suggest getting maybe some paper and pencil for writing these out. I think it's easier to write it than to type it for something like this. And as someone who typed it, yep, I definitely feel that way. Let's see here. Question 5. Apply De Morgan's laws. So that's something we covered in the very brief Logic 101 section of our intermediate modeling session. Apply De Morgan's laws to the following statements. Final answers should only include algebraic comparison symbols where applicable. So part A of question 5 is we have not Python or R. So again, De Morgan's law, essentially what it does is it sort of distributes the not within the parentheses and flips every or to an and every and to an or. So not Python or R is changed to not Python and not R. Part B says it's not the case that both x is equal to 0 and y is positive. Simplify the statement so all not are removed. So let's take the words and translate it a little bit more into symbols and variables. So we have not x is equal to 0 or y greater than 0. So x is equal to 0 is inside the parentheses. Y is positive inside the parentheses with a not on the outside. Let's distribute the not and change the or to and. So we have not x is equal to 0 and not y is positive. And then when something is not equal to 0, it is either strictly positive or strictly negative. And if something is not greater than 0, that means it is less than or equal to 0. So that's how we end up with our final answer here. All right, moving on to number 6. Let A be the amount of snow that falls overnight, and B is a binary variable indicating if school is open. B, in that case, B is equal to 1, or closed. In that case, B is equal to 0. Use this and the if-then to an or statement, so the logical equivalency of changing an if-then statement to or, to rewrite the following statement. If it snows more than 8 inches overnight, then school will be closed tomorrow. So let's replace the words with variables and notation. So if A is strictly greater than 8, because we're saying if it snows more than 8 inches, so if A is greater than 8, then B is 0, and that's B is school. Then school will be closed tomorrow. So then B is equal to 0. So now how you take a conditional statement and translate it to an or statement is you negate the first clause, so negate the if part, and then just copy down the then part, and then put an or in between. So the negating A greater than 8 is A is less than or equal to 8, and then B is equal to 0 stays the same with an or in between. So A is less than or equal to 8, or B is equal to 0. Question 7 is all about the contrapositive. We have a statement that says, if Duke is late for a meeting, that's because he was out surfing. So our if part says, if Duke is late for a meeting, and then part is because he was out surfing. So the contrapositive is negating both of these parts and then flipping their order. So we end up having, if Duke wasn't out surfing, then he won't be late for a meeting. All right, on to question 8. In the using big M constraints section of last week's notebook, we used the following inequality. X plus m2 times z is greater than or equal to c. Simplify this inequality, replacing m2 with c. So we start with the original. Switch this m2 to c, do a little bit of algebra and hocus pocus. And we end up with x is greater than or equal to c times 1 minus z. Part B of this says the other clause of this or statement was x is less than or equal to m1 times 1 minus z. Write out what these two inequalities reduce to when z is equal to 1 and z is equal to 0. So when z is equal to 1, essentially what happens is things what's happening in both in parentheses on both sides of this, so and both inequalities ends up being 0. Those zeros multiply by the constant c and the constant m1. So we end up with x is greater than or equal to 0. X is less than or equal to 0. Taking those two things together means x is equal to 0. Let's let z be equal to 0 now. So we're turning off our z switch, I guess. So let's replace z with 0. That makes each set of parentheses in the inequalities 1 times the constant c and 1 times the constant m1 yield both c and m1 respectively. So we end up with the inequality c is less than or equal to x, which is less than or equal to m1. And if m1 is large enough, that is essentially not considered a bound for x at all. And in our problem, in the widget problem, we sort of declared m1 to be the maximum amount that a certain facility can produce, the number of widgets, and c was the lower bound on what the sort of minimum amount that would be produced given that this value was positive. So this was the, hey, let's fix that really weird number in our original solution of sending 2 units from Cleveland to, I think it was Nashville. Okay, so formulation and coding section. In the constraint production facilities section of the Modeling 1 notebook, when adding the Y decision variable for opening production facilities, assume that there are fixed costs given by this list. For activating each respective production facility, write Gurobi Pi code that will add these costs to the original objective function. Well, the easiest way to do this is, in particular, this is kind of helpful when you have several different decision variables that contribute to an objective, is to, when you define the variable itself, you can just define the objective values that it has by using this obj parameter and just setting it equal to this list. So that's all it takes. You can definitely use the old-fashioned way, I guess, of the set objective command. One thing that is important to note about this is what we call model sense. And the default model sense for in Gurobi is minimization. So by default, if you don't specify if you're doing a minimization problem or a maximization problem, Gurobi will assume that you're doing a minimization problem. So when you're doing, or the problems that we were discussing with the widgets, they were all minimization problems. We were minimizing costs. So we didn't need to worry about setting what the sense was, because it was going to be that way by default. So if we were doing a maximization problem and we were to use this method of defining our objective function value, then we would also need to change the model sense to a maximization problem, so so Gurobi knows which way to go with it. All right, let's see, the last question here is question 10. Write Gurobi Pi code using indicator constraints, so my new favorite constraint, to model the following. And both parts reference decision variables in the modeling example 1 notebook, so they're all about widgets still. Part A is to use indicator constraints to model the link between XPD and YP. So again, the amount of widgets sent from production facility P to distribution location D. And YP is the decision to open or close production facility P. So part A, again, we sort of talked through this during the initial modeling session, during that presentation, and we came away with 2 ways of talking about this that were both logically equivalent. One is saying if XPD is positive, so we have, if we produce widgets at production facility P, and then it doesn't matter which distribution location we send it to, just anyone, as long as one of those happens, then YP needs to be equal to 1, meaning we open the facility. The contrapositive of that is if YP is 0, meaning if it's closed, then XPD must be 0 as well. And that's saying that if the facility is closed, then we cannot make any widgets there. So with the way that the indicator function works in Gurobi, that if part needs to be a binary decision variable. So given the contrapositive of sort of what we started it with as the original statement, if X is positive, then Y must be 1. The contrapositive of that fits into this nicely, saying if Y is 0, then X must be 0 as well for each production and for each P in production and D in distribution. Okay, so that was directly implementing sort of what we discussed there. And part B, you can just ignore the Z. We don't need that. Just scribble that out. So for part B, if Cleveland and Baltimore are open, so again, these are the Y variables, and the locations of the production facilities, then Charleston must be closed. So if Cleveland and Baltimore are open, then Charleston must be closed. Feel free to use auxiliary variables if you want. So if you want to use Z, go for it. You may have to change the index of it. You may have to add, for a production facility or for something like that. But it's there if you want to use it. But we ended up not using it. And there are a bunch of ways to do this, some of them with auxiliary variables. And it's one of the awesome things about mathematical optimization is the modeling part is kind of an art. There are more than one ways to do it. Some ways are more elegant than others, but and some solve faster, so some are strictly better in terms of performance. Some are strictly better in terms of interpretability from people reading it. So again, there are many ways to go about it. So one way would be to take that statement and take the contrapositive of that. You can see that there's a lot of nice logic stuff happening here, a lot of translating between if-thens and ors, and a lot of contrapositives and stuff of that nature. So if we take the contrapositive of that, that means we negate both statements, both clauses, the if part and the then part, and then switch them over. So that means if Charleston is open, because that's the opposite of Charleston being closed, then it's not the case that both Cleveland and Baltimore are open. So the idea that Cleveland and Baltimore are both being open means that both binary variables are 1. So that means y Cleveland and y Baltimore, when you add them together, are equal to 2. If they're not equal to 2, then given that they're both binary variables and all they can take is 0 or 1, if it's not equal to 2, then that means that their sum is less than or equal to 1. So the negation of that part of it is y Cleveland plus y Baltimore must be less than or equal to 1. So let's put it all together with our in our indicator function. So our if part is if Charleston is open. So if y Charleston is equal to 1, then y Cleveland plus y Baltimore must be less than or equal to 1. So that is it for our exercises here. There's a bunch of other ones. I think there's one more that I put on the original set that's sort of like a cool homework problem. I didn't bother putting the solution here, so it's something for you to noodle on, and maybe one day I'll post the solution in the event app, and we'll see who gets it. But definitely take a look at that, and it should be a fun little exercise. So we're done a few minutes early here, so we'll take another little break and meet up again in a little bit for our final session of the first day of training. So thank you very much, and we'll talk to you soon.